Okay, so we have a good overview of what we need to do. So let's think about how we could go about solving this problem now. So make sure everything is, what is this thing at the top? It's not good. Okay, so let's get that just to make sure it's nothing weird there. Okay, I don't know why that's there. It's cutting off here on my video, unfortunately. So let me just shrink this a little bit. Oh, that's part of the. Let me just restart this. Okay, this is perfect. Okay, so what we have is, this is the problem that we discussed earlier, previously, and I went through sort of just conceptually the steps that's required to solve this problem. So let's look at this solution to this problem. So first of all, the question is, we want to solve the weak form of the solid mechanics displacement problem, solid mechanics problem using a displacement approximation. And this approximation that I'm assuming here, I'm deciding on. So it's Nico's choice. And if you do it, I'll either tell you what the form should be, or it's a choice that we can make. Okay, so this is important to understand. This is not something that it has to be like this. It doesn't have to be a quadratic. It's a choice I make. First off, the reason I choose a quadratic is because when we do the finite element method, I'm going to do the most difficult 1D element first, and that's a quadratic element. And the linear one, I'm going to leave to you to figure out on your own. But what I make sure of is that what I do in class is when I tackle an element or an idea, I try to make tackle the most difficult version of that in class, so that you can sort of take the easier versions as practice to make sure that you're comfortable with them. Okay, so this is why I'm choosing the quadratic here. So this is the rationale. So essentially, I'm choosing for the displacement in the x direction, u, which is now a function of x, y, and z. I'm just choosing it as ax squared plus bx plus c. That's all I'm choosing. Okay, and I don't have any y terms or any z terms in there. They're all 0. And I will call these a, b's, and c's just the c vector. So c vector, that's what this a, b, and c stands for. Okay, so like this. Then v, as a function of x, y, z, I just choose the 0 vector. Yeah, so the 0 displacement in the y direction and 0 displacement in the z direction. I'm just choosing that. That's my choice. So please bear in mind, this is part of the question, is that we are going to assume this form. Okay, and we want to see, if we assume that form, what happens, what results? So automatically, just up front, if I were to apply tension to this bar, there would normally be, in real life, there would be Poisson's contraction, yeah? But by construction, because of the choices I've made here in the displacement, I cannot have any Poisson's contraction. There is no, when I apply some displacement in the x direction, or force in the x direction, this wants to contract in y and in z. But now by construction, I'm eliminating that option. It's impossible, okay, because of the choices I've made here. And so based on these choices, what is the best we can do? Okay, so just bear in mind, this is just important to make sure that we're comfortable with that. Okay, now that I've got sort of the displacement fields, and that's given for us, or that's a choice we've made, depending on how I want to view it. But what I cannot negotiate on, and this is where we're doing the Bipnov-Galerkin approach, is that the weighting functions will have exactly the same form. Different coefficients, but the same form. So the weighting function for u must have the same form, so it must be a quadratic function as well. And I'll call it dx squared plus ex plus f. Okay, so that's the same form. The weighting function for the displacement in the y direction must be the same as this, so I must choose it 0. The weighting function for the z displacement must have the same form as this, I must choose it 0. So that's equal to 0 here. I don't know if you can see that. Somehow my pen didn't put it in, but there's equals to 0 here, as you can see. Or if you can't see it, just write it in. Okay. So that's essentially what this W, the subscripts UV and W will relate now towards sort of the UV and W fields, the respective displacement functions for which they are mirror functions. So these weighting functions. Okay. So for short-hand notation, I'm again going to put the DE and F into a W bar, a W vector. So that's essentially that. And then also, just to keep things shorter, the x, y, and z I'll just write as x with a vector. So x vector, things you should think of as x, y, and z now. Okay, that's what I have. Now we've got the weak form. So this is the weak form of the solid mechanics form. That's from the concept cards. You can open the concept cards and double check that this is correct. The stress tensor double contraction with the weighting functions gradients. Then essentially have the traction dotted with the weighting function, and the weighting function dotted with the body force. And this is area integral, this is a volume integral, and this is a volume integral. From the Voigt notation, relate stress to strain. So this is algebraic relationship. This is a partial differential relationship. Here are the prescribed displacements, and there are the tractions. that we, the prescribed displacements, the W's must be 0 when we have prescribed displacements. That means that the displacement will exactly satisfy the prescribed displacements. It won't be approximation. Okay. So first off, let's do it systematically, step by step. Let's first tackle this first term. Let's take this first. If we tackle that first term of the integral scalar, I've got the stress takes a double contraction with the gradient of the weighting function. That's what we had there. Remember, go back to the concept cards if you want to remember what this means. But this is just multiplying this with this. Sorry, dotting this vector with this vector. So it's this multiplied this plus this multiplied this plus this multiplied with this. Then this multiplied by this plus this multiplied by this plus this multiplied by this. And we just continue until we have sort of a scalar out. Okay, so this is what I'm going to do here at the bottom. Make sure that for this stress tensor that we have here, if we write everything out, okay, so that we just first get to that point, and then we can start seeing what do we have. So first off, sigma xx will multiply with this, plus shear will multiply with that, plus the other shear will multiply with that. And then this is sort of all of those terms just written in one go. You can just double check for yourself to see that this multiplied by that, plus this multiplied by that, plus this multiplied by that. You can see that all those terms are there. But because we've already made choices here of the displacement for V, of the weighting function for V and the weighting function for W are both 0, so we can start deleting stuff here. Wherever we have sort of a weighting function V and a weighting function W, a weighting function V, a weighting function W, we can make all of them just 0. So just start with that. V, the derivative with respect to x is also 0 if the function itself is 0. So that's 0, that's 0, that's 0, that's 0, that's 0, that's 0. Plus this WU function, which is a function of x, y, z, is only a function of x. So any variation with y and z will also be 0. So I can say any variation with y or any variation with z will also be 0. And so I'm only left with this term here. Sigma x multiplied by the partial derivative of weighting function u with respect to x. That's all. That's the only non-zero term that we have. So this whole thing reduces to this, simplifies to that expression. Beautiful. Okay, so that's the first thing that we have. Next thing, we know that stress is related to strain. Yeah. So we can easily, So before we do this stress to strain relationship, which is sort of just this work notation version, this is just a stock standard 6x1 in the material matrix that I've got here. I don't know why I did this version here, because I wanted to do it sort of in reverse, I think. So let's just start off then by saying what we know. So what we know is essentially, let's look at the strain. So this is now the strain related to the displacement in a sort of intuitive way. We know that we've assumed for the vertical displacement to be 0, and we've assumed the vertical displacement z to be 0. So what that means is essentially is the following: that certain terms will just essentially evaluate towards a 0. Yeah. And what it means is that the Poisson's ratio contraction that we have here, we can specify, but it will not do anything per se for us per se. Yeah. So our choice of our displacement field is implicitly assumed, because we don't allow for any contraction, that our Poisson's ratio factor is just 0. So this is an assumption that follows because of the choices of the displacement field. We can imagine that we want to put values in there, but it's essentially we have forced this Poisson's ratio factor to be 0 by the choices we've made in terms of saying that we only have a variation of this displacement can only vary in the x direction. So this we can simplify by saying let's plug in the Poisson's ratio 0, 0, 0, 0, 0, 0, 0, and then this is just a reduced thing. Okay, so that's sort of the argument. Just sometimes when we make choices in terms of the function that we approximate, they might have unintended consequences. Okay, so this is one of them. This is an example of an unintended consequence because of the choice of the displacement fields that we've made. Okay, but more importantly, what I want to relate here is get to the point of what is the relationship between the stress and the strain. Okay, so when we get to this, we see essentially that the stress is now related to strain by E only. So we can see that this is sort of the relationship that we'll have there. Sigma y with respect to epsilon y, do that. But what we know already up front, and this is what the next page will do, is just because of my choices of v and w being 0, I know that this will be 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 0, and I know that this will be 0. Okay. So the only thing that will not be 0 is that term there. That is essentially because of this choices, as well as the fact that I know that u is only a function of x, not a function of y and z. So that's the only non-zero term that we'll get. But let's do that formally. Okay, so let's write it out formally, go through this displacement gradient approach. So already we know what to expect for the answer, so we can just double check that we get something that's sensible. We know that the strain matrix is related to displacement by taking the gradient of displacement plus its transpose multiplied by half. Let's do that. So the displacement in u, v and w is just this. This is the vector that we have there. Let's go and compute the gradient of this. So the gradient of u with respect to x, y, and z. So x is this. Derivative with respect to y, the partial derivative with respect to z is that. Same for these and same for these. So this is the partial derivative of v with respect to x, y, and z, w with respect to x, y, and z. And now I can say u transpose plus u, add the two together, multiply by half. This is my strain matrix from my assumed displacement field. Beautiful. And now I know, because my strain matrix has the epsilon xx term here, and I know that's essentially the only non-zero term that I have, because we already reasoned about these to be 0, but now we see that they're also 0, that the diagonal terms for v and w in terms of strain yy, strain zz is 0, and all the shear terms are also 0. So the only non-zero term that I have is sigma xx is equal to e times 2ax plus b. This is what I have here. Okay. And also, I can go and compute. Just go back to that expression. I can compute this. The derivative of w u with respect to x is 2 dx plus e. That's essentially what I have there. Okay. So I can now multiply this. So this is my expression for sigma, the double contraction with the expression for the partial v w partial x. That's what I end up with a double contraction scalar kind of equation. Beautiful. Step number 1. Okay. Now this is the volume integral, and so now what we can do is say what we have here already in this problem is we know that the area varies linearly. It's given to us, so we can write this volume integral as essentially an area that varies as a function of x times dx. So we can just rewrite this dv to be how the area varies as a function of x times dx, because this is what's given for us. We're not given the area as a function of anything else, x, y, z. It's just the way it's given to us is that a varies as a function of x. So this allows us to relate this. Okay, so I can then say, okay, fantastic. This dv that I've got here, I can substitute by ax times dx, and this is what that is. Okay, so this is the expression, and then I can integrate from 0 to 1. So I've converted the volume integral into a one-dimensional integral by introducing the area variation. Okay, at this stage in the problem, E is given to us as a constant. So this system E is just given as 210 gigapascal. It could have also varied as a function of x. Then we could not pull it out of the integral, but because it's a constant, we can pull it out of the integral. So this is what I'm doing here, pulling it out of the integral because of the constant nature of that. Okay, that's first term is this that we've got. And we know later on we're going to take a derivative with respect to d and e, and that will give us a linear system of equations to solve so that we can solve the problem. Okay. Let's look at the second term. So what I'm talking about when I say second term is, this is the left-hand side that we've got. Let's look at this traction term here. So that's a traction t dot w. So it's a traction vector w dA, and that's where we apply tractions. We apply tractions at that right edge. Let's go. So the second term, the tractions are applied at x equals to 1. That's where we apply tractions, okay? The traction is just the force over the area, so we need to look at what is the area evaluated at x equals to 1. Not the area everywhere, just at x equals to 1 where we apply the traction. And if I do that, then I can work out that the traction is 10 megapascal. Okay, that's the traction that's applied to that size. So that is the sort of the non-zero component that we have. That's the traction in the x direction. The traction in the y and z direction is 0. So I can put that into my traction vector, 10 megapascal, 0 and 0 for the y and z. And then I can say we have to multiply this, dot this actually with weighting function, weighting function, sorry, that is written in the vector form. So that's now WU, just shorter notation, but not the weighting function anywhere where we apply the traction. So I have to evaluate the weighting function at x equals to 1. Okay, so that's essentially saying this becomes now d1 squared plus e1 plus f. Okay, so that's what we have there. And then, again, when I look at this dA term that I've got here, I have to ask myself, what is the area? So I have to integrate this now at x equals to 1. What is the area at x equals to 1? And this traction is just uniformly distributed because I just divided here by the area at x equals to 1. So essentially, if I integrate the traction at the place at x equals to 1, I just take this traction and I multiply it back by the area evaluated at x equals to 1. So this is what this dA at x equals to 1 just really becomes the traction dotted with a W multiplied by the area. So if I integrate now over dA, that is now integrated technically over x, y, and z, but I know that all I'm given is what is the area at x equals to 1. So that is essentially what I get out there. And this is what I have then. Okay, so this evaluates then just towards the traction of 10 megapascal multiplied by the area at x equals to 1, which is just, again, I get back the 10,000 newtons of the force that I've applied there. So that traction integrated over the area becomes, again, just a force multiplied by d, e, and f. Okay, because this is an area integral at x equals to 1. Please take note of that. Okay. This is then essentially the first, this is now what I have. I've got now, let's go back, term 1, term 2, and this term is just 0 because this body forces are just 0, 0, 0. So that will just fall away. So this allows me to have this now. Beautiful. Now I can go and say where we have prescribed displacements. Where do we have prescribed? Only at x equals to 0, at the left-hand edge. This is where we have prescribed displacements. At the place where we have prescribed displacements, we know for a fact that where we now, so where we have prescribed displacements, we know for a fact that we can evaluate u equals to 0. This is our expression for our displacement, u, and then see what happens to the coefficients. So if I plug in x equals to 0 into my expression ax squared plus bx plus c, but x equals to 0, then it becomes 0 plus 0 plus c. That is that, and that must be equal to my prescribed displacement. The fact is it's clamped, so it's 0. So this implies that c is equal to 0. Plus, everywhere we have prescribed displacements, irrespective of the value that I apply there, the weighting function must evaluate to a 0 at those places. That's important. So if I plug in x equal to 0, my weighting function, f is also 0. So already I've solved 2 of the coefficients. They disappeared, and now I have only got essentially these 4 unknowns related, and I know I'm going to get rid of these 2 by taking derivatives with respect to d and e. And then I can solve for a and b. So I expect to end up with a 2x2 system at this stage. All right, so let's go. This is my weak form now. In current form looks like this. Can you imagine? All of that beautiful mathematics and calculus reduces to this very basic expression here. And now what we're going to do is, and this is the key of the finite element method, this is one of the things that makes the finite element method so useful, is we're going to convert this now into a system of linear equations by taking derivatives with respect to d and e, like we've done before. So we can recover a system of equations by, like I said, differentiating by respect to d and with e. Okay, we know f is already 0 and c is already equal to 0. And if we were to take derivatives with respect to e, d, and e of this, then essentially we end up with this little 2x2 system of equations. This is what we end up with. And you can confirm it for yourself to say, if I take the derivative of this expression with respect to d, I end up with 2 times 2 times x. Yeah, that's essentially what this expression would lead to. 2 times 2 times x, so this should be then 4x squared multiplied by the a still, and this is integrated over 0, 1, and this is then multiplied by a. That's what happened to that a. We just pulled it out here. But what you see is the derivative of this expression with respect to d is just merely 2x that gets multiplied by this. Okay, so that's the 4ax squared. That's that term. And the b term is essentially just the 2x that multiplies by the b. So that's the 2x multiplies by the b, and then still integrated by the area. That's that part there. If I take the derivative of this, so this is the first equation that I've got on this side. And if I take the derivative of this side with respect to d, I just end up with 1,000. Beautiful. This is my first equation by taking derivatives with respect to d. If I take the derivative with respect to e, what I end up with is the following. The derivative of this expression with respect to e is just 1. So I end up with 2ax times the area, integral of the area dx, and then this term here gets multiplied by 1. If I take the derivative of this with respect to e, which is just the 1, then it's essentially just this integral times b. This b will multiply with that. That's what we have there. This is the second equation. And if I take the derivatives on this side with respect to e, I end up again with just 1,000. So this is my small system that I have. Before I can solve this, I first have to integrate. So I do need to do this integral, I need to do this integral, I need to do this integral, and I need to do this integral. And these integrals you can do. In the beginning, we can sort of do it by hand, or in the list with SymPy, just to make sure that you're comfortable with them again. But this is really, again, basic stuff, basic polynomials. This is first year mathematics at university, so it's something that you've done now so many times. So you can integrate this integral, this integral, and this integral, plug it into the system, and see